Today we're going to talk about parabolas. We talked about parabolas earlier this year as being the graph of a quadratic function. Throughout this chapter, we're going to be looking at what are called conic sections, which are different types of graphs of quadratic equations, but not necessarily functions. So earlier this year when we studied our parabolas, they were equations that were like y equals x squared, and our parabolas looked like this. In this lesson, our parabolas will also be allowed to face sideways, so that means that they would not be a function, but we're going to be okay with that in this chapter. Okay, so earlier this year, we need them to face up and down so that they pass that vertical line test. In this lesson and throughout this chapter, our graphs may not pass that vertical line test, so they might not be functions, but that's okay. There are 4 different types of conic sections that we're going to study. Graphs of parabolas, circles, ellipses, and hyperbolas. And after we've looked at what those 4 are, then I'll tell you why they're called conic sections, kind of all together once we've seen what each of them is individually. So a parabola, it says, is a line in which every point on the parabola itself is equidistant, or the same distance, from a point called a focus and a line called the directrix. Okay, so I'm going to graph out what this is talking about. So, I'm going to plot out some points that I know will lie on a nice parabola here. And then if I could only connect the dots. But, so this is a graph of a parabola. And how a parabola is defined in terms of being a conic section is it is a line so that any point that I take is going to be the same distance away from a point called the focus and a line called the directrix. So I'm going to put my directrix here and my focus there. So a focus is going to be a point that is within the figure, and the directrix is going to be a line that's opposite of the focus. Then any point that I pick on this thing should be the same distance away from that point in that line. So the vertex is the easiest to spot. It's 1 away from each. Okay? But if I take this point over here, it doesn't look like it works, but it should work. Or if I take this point over here, it should be the same distance between those. So a parabola is defined as any point that we take on it, the distances should be the same to the focus and the directrix. So this one isn't actually a great parabola to illustrate that. But that's how a parabola is defined. So we have this chart here. This chart is going to be your best friend while you're doing your homework. You don't need to memorize the values found in this chart or any of the equations or anything like that. You can use it while you're doing your assignment, and when we come to the test, we'll have a version of this chart that gives you what you need. So there's 2 different forms of a parabola. The first one, the first column says its axis of symmetry is vertical. That means these ones are facing up and down. So the middle line that we could fold it over is a vertical line. The second column then is where axis of symmetry is horizontal, or that I would fold it over a horizontal line to make it equal. So for the vertical form, our equation is going to be x squared is equal to 4py. For our horizontal, then our equation is going to be y squared is equal to 4px. Then we can see what point is going to define our focus and what line will define our directrix then. So for the first problem, it asks us to identify the focus and the directrix and to draw the parabola. So first thing we need to do is get this thing so that it looks like one of those 2 forms of the equation. In either of the 2 forms, the squared thing is alone. So for our parabolas in this section, we're going to want the squared thing to be alone. So in this problem, I need to get the y squared alone. How do I do that?
Add 1 6.
Multiply by negative 6. I'm going to get negative 6x is equal to y squared. So now when we look in the chart, one form of the equation says that y squared is equal to 4px. Is this going to be a horizontal or a vertical facing parabola? It's going to be a horizontal. The y squared is going to create the horizontal. So by looking in the chart, we can see if the top row of the chart says it's the y squared, the bottom one says that it's the horizontal facing. Now what we want to do is in this equation in our problem, the purple one, and in the standard form equation, the orange one, we want to match up the -6 and the 4p, because everything else already matches. The y squared matches, the x matches, so that means that stuff that's circled, it should match, or it should be equal. So -6 should be equal to 4p, which means that p is equal to what? How do I get to p alone? Divide by 4, so we get -1.5. That p-value is important because in the chart, that's how we define our focus and our directrix. So in the chart, we are told that for a horizontal facing, the focus is going to be at p, 0, so -1.5, 0. And the directrix is going to be at the equation x is equal to the opposite of p, so that'd be positive 1.5. For this lesson, all of our parabolas are going to have their vertex at the origin, at 0, 0. Okay? Later in the chapter, we'll talk about how to move that vertex around to a new location, but for this section, all of them are going to have their vertex at the origin. So we were asked to identify the focus and the directrix, and then also to graph. So now to graph this. The vertex is going to be at the origin, so we're always going to have a point at 0, 0 in our problems today. Then we want to plot our focus. Our focus is at -1.5, 0. So that's on our x-axis at -1.5. Our directrix is at x equals positive 1.5. Our parabola is then going to go through the vertex around the focus. It's going to open up like this. You're just going to sketch it around that point, but one thing that you should attempt in your sketches is getting a somewhat appropriate width. The p-value is what determines the width. The larger that p-value is, the wider the graph is going to be. Okay, so 1 is considered just kind of like a medium width. This is larger than 1 since it's 1.5, so that means this one should be a little bit wider. Okay? If we had a small p-value like 0.5, then we would expect a narrow parabola. But we're not going to plot any exact points to determine the width. But big p-value, make it wide. Small p-value, make it narrow. Okay, and 1 is kind of the middle. And then again, the definition of how this works is if I take any point on this thing, the distances between the point to the focus and the point to the directrix should be the same. We can see that a little bit better in this graph. I picked the wrong focus and directrix in the other problem. That's why it didn't really work out so great in my other graph. But here we can see a little bit better that the distance to the focus and the distance to the directrix should be the same for any point we pick. Okay, look at another example. Same thing, we want to find our focus and our directrix given our equation. First step is we need the y squared alone. You need whatever is squared alone. So whether it's x squared or whether it's y squared, you need the squared alone for the standard form of a parabola. So how do I get the y squared alone? Multiply by 4/3. That'll cancel that out over there. And over here, we'll get 4/3 x is equal to y squared. Is this going to be horizontal or vertical facing? Horizontal facing. A y squared is under the horizontal column in the chart. And our general form is 4p times x. So that means whatever that coefficient is should be equal to 4p. So 4/3 should equal 4p. So how do I solve for p? Divide by 4, which is the same thing as like multiplying by 1/4. So that gives me then 1/3 is our p-value. So then according to our chart, our focus for a horizontal facing is going to be at p, 0. And the directrix is going to be at x equals -p, so -1/3. To draw this, our vertex is always going to be 0, 0 today. The focus is over just 1/3. And the directrix is back just 1/3. One-third is a small p-value, means that this graph should be a narrow parabola. I use 1 as kind of medium. Smaller than 1, make it narrow. Bigger than 1, make it wide. Questions? Your p-value can also tell you the direction. A positive p-value will face up or right because those are positive directions. A negative p-value would face down or left because those are negative directions. So by looking at the p-value, we can tell both the width and the direction of our graph. Our last two examples are going to do the opposite. Here we have the graph and we want to find the equation that would have worked for this. So is this horizontal or vertical facing? Vertical facing. So opening downward, which is a vertical direction. So then our equation in our chart is x squared equals 4py. We're given our focus. The focus is at the point 0, -3. And we're told for a vertical facing that our focus should be 0, p. That means p is equal to -3. So in the equation, I'm going to plug a -3 in for p, which gives me x squared is equal to -12y. Okay, and that's all there is to this one. Again, the p-value can tell us a couple of things about it. Because we had a negative p-value, we have a downward facing, because down is a negative direction. And with that p-value of 3, this graph was opened very wide. Questions? Is this one horizontal or vertical facing? Vertical facing. So vertical facing, our equation is x squared equals 4py. In this one, we're not given the focus. We're given the directrix is at the line y equals -2. In the chart, it tells us our directrix should be at y equals -p. So that means p is equal to 2. So we plug 2 in for p. We get x squared is equal to 8y.
Please excuse this interruption. Anyone involved in praise band this morning, please go down to the cafeteria.
Again, the p-value can tell us a couple of things about our graph. Since we got a p-value of 2, we would expect an upward-facing graph because 2 is a positive value. Should face upward then. And with a p-value of 2, that's larger than 1, so we should expect this graph to be more wide than it is skinny. So this is a wider-facing graph.
So you always want to read it as x squared.
You always want the squared thing alone. Yeah, we're not going to be solving for y equals equations with conics.
How do you know if it's negative or positive?
If what's negative, positive?
If the
The directrix? Well, the directrix is at a value of -2. And the equation for directrix is that y equals negative p. So then the negatives are already matched up, so then the p must be the 2. Also, the fact that it's upward facing means that we should have a positive p value.
do you always tell whether it's facing up or down? That should be your indicator.
Yes, so up and right will be positive p value, left and down will be negative. Okay, so your assignment is from 10.2 tonight.